Hello everyone, my name is Bagus Santoso. I would like to present my work. The title is Generalizations of Isomorphism of Polynomials with two secrets and its application to public key encryption. So the agenda of this talk is follows. I divide the talk into 7 parts. Let us start with the background. As we know, the multivariate polynomials-based cryptography schemes are one of major candidates for post-quantum cryptography, and many promising constructions for synthesis schemes like rainbow signatures, etc. However, in public key encryption schemes line of research, it's not that promising. We know many multivariate polynomials-based PK schemes were broken very fast, sometimes only a few months or years after publications, especially the schemes based on the hidden field equations or FSE paradigm. So let us look into this SFE. The standard procedure in SFE-based schemes, first we need to prepare a multivariate polynomial f, which is easy to invert, and mask it with hidden invertible linear maps SFT. And we compose a function g using ft and s as follows. And we make g as public key, t as f as the secret keys. The common pitfalls in SFE-based schemes actually, because the main assumption in SFE actually is supposed to be hard to find f, s, and t given g, but it turns out that in many SFE-based schemes that it is easy to find f, s, and t from g. What is the cause? The main cause, in general, because the SFE schemes requires f to have a special structure to guarantee that it is easy to invert. But it is these special structures that actually become the culprit, because it enables kind of efficient reductions into an easy instance of min rank problem. Before we go forward, I want to summarize the results of my paper. So in this paper, we propose new computational problems based on multivariate polynomials by generalizing the problem of finding isomorphism between two multivariate quadratic polynomials. And these problems, these new computational problems, offers flexibility on controlling the number of unknowns and available equations, so that the problem is hard in practice. And also, they allow the kind of a Diffie-Hellman like structures, and such that we got a new paradigm, which is a non-SFE paradigm for constructing PKE schemes based on multivariate polynomials. And let us see the challenges on constructing TS-like structures in multivariate polynomials. First, I want to introduce the foundations, the foundation of all the foundations that of our results, that is isomorphism of polynomials with two secrets, or IP2S problem. IP2S problem is given f and g, which is a multivariate quadratic functions family, and each f and g actually a set of quadratic functions with the following form. And given fg, the problem requires us to output invertible matrices T and S, so that we can compose G like this, which means that G is an isomorphism of F. So if there is isomorphism between G and F, so we require to output it. This is the problem of IP2S, and this problem proposed by Patron in 1996, and for Green Parrot in 2006 proposed polynomial time parallelism to solve IP2S in special case set called inhomogeneous MQ. In homogeneous MQ, in this inside this F, actually there's at least one quadratic functions in F have structures such that the coefficient of the linear and the constants are not zero. 2013, Bollinger et al. Proposed another algorithm to solve IPTS with homogeneous MQ in exponential time. Homogeneous MQ means that all polynomials functions in F only have the degree 2 coefficients. So this is the best result of solving IP2S in homogeneous MQ. So let's see, before we go to Diffie-Hellman structure on IP2S, I want to review again the original Diffie-Hellman. So basically, in original Diffie-Hellman, we try to construct kind of common key by crossing the public key of one party and secret key of another party. So like this, we have public key and secret key with this, and public key and secret like this in two different parties. And by crossing the public key and secret key of different parties, we compute a kind of value g to the power s2, s1, to g to s1, s2. And thanks to the commutative property of s1 and s2, and we got a common key here because this value, the left and right are actually the same. So we want to recreate this commutative property, and fortunately we have circular matrix which have commutative properties. So we set the secret as a circular matrices here, and by using crossing functions, and we have this value in the left and the right. And thanks to the commutative property of these circular matrices, we know that this left and right are the value actually the same. You can see here the order actually does not matter. It's not matter. No. But this construction actually is not secure at all, because if we have the circular matrix, we only the first row can define the whole matrices. So the number of unknowns is quite low. While to the result by Vogel and Perret, we have this number of quadratic equations to solve these systems. And Courtois et al. In 2000 proposed this in equations. If the number of equations and the number of unknowns satisfy this in equation with some constant epsilon, positive constant epsilon, then the complexity to find the unknowns using relinearization algorithms, actually the number of unknowns raised to the order of the 1 divided by square root of this constant epsilon. So we put this number of unknowns and this number of equations into this in equations, and we got as follows. So you can see that by putting epsilon to the 1 per 4, this equation is satisfied, which means that we can solve this problem in polynomial time, because epsilon is only 1 divided by 4. It's quite large. And this pitfall is quite common, and Wang et al. Propose a similar kind of scheme, and using directly circular matrices for his schemes and their schemes, and it's just broken in within 2 years with the same analogy. So actually, in using circular matrices as secret, we need a delicate control of number of unknowns and equations. We want to introduce another attempt here. That is we call it multi IP2S. So instead of having one problem of instance of IP2S, we have several of them. So we have a K here. So and we are required to solve this all K problems simultaneously. So here we can calculate the number of unknowns increases, also the number of equations as well. But when we put this equation into the Courtois equations, we know that by setting k equal n, we can have that complexity to solve this system using realization of Courtois is actually exponential. However, is it really true? Unfortunately, it's not true. So actually, because this system, instead of solving them simultaneously, we can solve them separately one by one. Yeah. And because solving one problem is polynomial, so the complexity of the whole uh, problem is actually polynomial time. So just by increasing the number of problem instance will not solve our problem to have it's just it doesn't mean that it's secure. So our research questions is that we want to know how to redesign the IPTS problem such that first we can control the number of knowns and equations appropriately, and second we have the Diffie-Hellman like structures. The basic idea is as follows. So first, to make it to have separable instances is not good. It's a bit a bad idea. So we made it inseparable. So instead of just releasing them like this, we sum them all into one line, so that the problems become inseparable. And then we know that we can make it the complexity using relation become exponential time. But we lose the DH-like structure. Next is our discovery. So here, instead of have one line here, so actually we define new notations for simplicity. So this actually psi I here is the pair of the secrets DNS, and the operations of star operations of psi on F is actually the compositions of this. And the larger matrix psi without index actually the arrangement of this pair of these pairs of matrices into a circular manner. So you can say it's a rotating. So one here is diagonal is same and it's rotating each row. And the under operation we call box asterisk. So this matrix psi operates on F means that the summations not only once but several summations, but the elements here of the summations is arranged in circular manner. So you can see here is the psi1 operate on F1, F7 of F2. Psi1 is all on the same the same diagonal. F2 also, psi2 also. And actually, by this we can get back the DS-like structures. So for example, we have psi and phi with this arrangement, and we have F as a multivariate polynomials. When we operate first psi on F, then phi on phi after that, actually the result will be the same. We operate phi first to F and then psi. So we got back the DS structures. And actually, we also by analyzing the number of unknowns and equations, we know that we can set k to the value such that the complexity of solving this system using realizations become exponential. And we also based on them, we propose new problems which are analogous to discrete logarithm problems and computational Diffie-Hellman problems. So the first problems which is analogous to discrete logarithm problem is as follows. We call it the BIPC problem. So given f and g, the problem requires us to output psi such that psi operate on F will result on G. And the computational Diffie-Hellman BIPC, CDS BIPC is as follows. So we have F1, F2, F again G1. All of them are from the multivariate quadratic polynomials, such that G1 and F1 have relations connected by psi, and we require the problem require us to output another multivariate quadratic polynomials G2, which have the similar relations to F2. So G1 and F1, the relation between G1 and F1 should be the same with the relation between G2 and F2. So based on these problems, we applied to construct a new public key encryption scheme. So in keygen, basically is the application of BIPC. So psi is the secret key, and operation of psi on FFG and FG become public key. Encryption is as follows. Basically, it's just like Abdul Al-Gamal. And so we have FG as public key here. And first we take a random phi, and phi operate on F as C0, and C1 is a encoded plain text summed by the result operation of phi on G. And C0 and C1 will be our ciphertext. And integration part using the secret key psi by decoding the result of C1 minus the psi operator on C0, we got the plain text back. Next, we show how it actually this scheme really satisfies the completeness. So we analyze the inside of this. So C1 minus psi operate on C0. So if we, according to schemes, we can expand this into like this. And the most important thing is here, because in this part of the phi operate on G can be expanded to phi operate on the result of between psi operate on F, and we can reverse order between psi and phi here using the main lemma, which is the DH structures. And because this part, as you see, in this part actually the same, so we can cancel it out and get the encoded plain text. So these schemes satisfy the completeness. We also prove that if the CDS BIPC is hard, then our PQ scheme is actually one-way CPA secure. So let's go to the parameter estimations. So the simple realizations might not work because we have set the number k so that it will be exponential time, but there might be other methods. So we estimate parameter based on several attacks. So first attack is the heuristic attack based on the Boyle-Laguerre et al. First, we transform the problem instant from homogeneous to inhomogeneous MK. Then we use the algorithm by Folger and Parrot to solve the transform problem instance. The completion of transformation is like as follows. But however, actually we have to note here, but actually we ignore the fact that the algorithm by Folger and Parrot is actually for original IP2S problem only. And without any proof, actually we also assume that the algorithm can work on BIPC problem instances. So for a real attack, you have to solve this. Another is the direct attack using kernel base. And we assume here actually we can ignore the T1 to Tk part and transform the BIPC problem into problem of solving quadratic polynomials with these unknowns and quadratic equations. And we use the asymptotic complexity of solving the quadratic equations by Bardet and all. And the last one, we taking into account k-sub attack. Unfortunately, this attack we just discovered recently, so that we haven't put it in our paper. And actually, the alternative security parameter table 2 in our paper, which is in PQCrypto, is actually insecure against this attack. So we will put the updated parameters in our ePrint version or in ICR as soon as possible. So this is our the table of our parameter estimations. So in conservative one, we take into account all attacks, but in the relative, we only take care of direct attack and case of attack. And also we also propose what we call aggressive variance, where we set the whole f1 to fk into the same polynomials, into the same set of polynomials. And you can see that the the size of probability instance here actually will be the size of the keys in our PKE scheme, and the size of solution here actually will be the size of secret key. This is here is actually quite large. That's why we propose the aggressive variance. So we go to the last conclusions. So we have proposed new computational problems based on multivariate polynomials with DS-like structures, and based on it, we propose a new paradigm to construct provable security scheme. We only prove the security in one-way CPA, but you can upgrade easily to distinguish CCA using generic transformations like Fujisaki Okamoto transform. And actually, our proposed parameters are very conservative, as you have seen. So actually, some small secure parameters will be highly possible, but we need more analysis on it. We will continue to update our new results in our ePrint version at ICR, and we hope that it will be released soon. So stay tuned. Thank you very much for listening to watching these presentations, and please send any questions or comment to this email. Merci beaucoup. Thank you.